All right, so let's pick up right where we left off last time. So last time we were talking about some of the basic ideas of thermodynamics, such as enthalpy, entropy. We defined some of these terms. And we left off talking about entropy. So we left off just setting up the idea of entropy, talking about what processes are allowed, which are not. Remember that entropy for the universe, we always want that to be increasing. Okay, so don't forget those ideas we covered last time. But now we're going to take those same ideas, and now we're going to start to put them in terms of molecules, so the molecular interpretation. Okay, so we're going to start off by just looking at a simple little diagram here where we have two gas bulbs connected with a valve. Okay, and so we have two gas particles, a red particle and a blue particle. And we're going to talk about the probabilities of finding them in various states throughout this little apparatus. Okay, so we're going to talk about probability. Okay, so the probability of finding the red molecule in the left flask would be 2 out of 4. Okay, so we have 1, 2, 3, 4 different possible states here. So 4 different probabilities in total. But if we look at only those that keep the red molecule, or the red atom you could say, in the left flask we have this one, and we have this one. So 2 out of the 4. Okay, so our probability of finding the red particle in the left flask, or left bulb, however you want to say it, would be 2 out of 4, or 1/2. Okay, so 1/2 of the time, the red particle can be found in the left side. The red particle can be found on the left side. Okay, what if we're talking about the blue particle being in the left flask? Okay, now all we have to look at, here we have this one, and we have this one. So very similar. So 2 out of the 4 times, so 2 over 4, or 1/2. So 1/2 of the time, the blue particle will be in the left flask. Now what about both of them being in the left flask? Okay, so here we just have 1. Okay, so we have 1 probability where they both occur in the left flask. So 1 out of 4. Okay, so 1/4 of the time, both of them will be in the leftmost flask. So if we had one more molecule, probably all 3 being in the leftmost flask would be 1 over 8. Okay, so what's the point of this? The point of this is we're talking about different probabilities of different states of each molecule, or the atom or molecule particle, however you want to say it. Okay, so if we had one more, okay, we would actually have a lot more probabilities here. Okay, we would expand on, okay, so sometimes it would be in the left, sometimes it would be right, sometimes the blue and the third particle would be in the left. You can kind of get the idea here. But the point is, every time we add another degree, another variable, we decrease the probability of finding that particular state. Okay, we decrease the probability of finding that particular state. Okay, and we're going to carry this idea forward with us. Okay, and we're going to use this to sort of as an interpretation of entropy. Okay, if we had n molecules, probability would be 1/2 over n, where n is equal to 6.02 times 10 to the 23rd, so our Avogadro's number, which is essentially 0 probability. Okay, if you're wondering where the 1/2 comes from, it's because we have 2 different flasks, right? Okay, so moving on. So this is what's called statistical thermodynamics, which is the use of statistics and probability to link macroscopic and microscopic scales. Okay, so in other words, it's a way of applying the properties of bulk matter, so it's an entropy. It's a way of using those to explain statistical distribution of the atoms and molecules making up the matter. Okay, so it's a way of interpreting how the bulk matter is made up by using bulk properties, but applied to small parts of the matter, applied to the atoms and molecules that make it up. Okay, so we're taking a bulk property, but we're applying it to the smaller subparticles or smaller matter that make up the bigger matter. Okay, this is what we call microstates. Okay, so Boltzmann used statistical thermodynamics to study the motion of molecules. He envisioned the placement of the molecules in a system at any given instant in time as a snapshot. Okay, so it's like taking a picture of a molecule or a set of molecules or set of atoms. Okay, and he called these microstates. And we give these the letter W, capital W. Okay, so he believed there was a relationship between the system's entropy and the number of microstates. So he said that the entropy of the system is proportional to the number of microstates, which again is given the letter W. Okay, so what he's doing here is he's using this idea of, just like we talked about with the particles in the flask. Okay, so he's kind of taking a snapshot of the molecule and using that to say, okay, I can measure the amount of entropy in that system or in that molecule by using that snapshot, and we're going to call that a microstate. And we're going to look at how many different microstates could I have, and we're going to use that to interpret entropy. Okay, so he said the entropy of a system is directly proportional to the number of microstates. Okay, so he has this equation here. So entropy of the system is equal to some constant times the natural log of W, which again is the microstates. And here K is the Boltzmann constant, which is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Okay, and we can make a state function out of this. So we can say the change in the entropy of the system is equal to that same equation, only this time we're talking about the final microstates, minus same equation, but talking about the initial microstate. Okay, and we can pair these together and we can say that the change in entropy of the system is equal to the Boltzmann constant times the natural log of the final microstates over the initial microstates. Okay, and we can use this to interpret our entropy now, our change in entropy. Okay, so if our microstates that we end up with are the same as the microstates we begin with, okay, delta S is going to be equal to 0. Okay, since the natural log of 1 is equal to 0. So remember, we're taking the natural log of this equation, or this portion of the equation. Okay, when we have more microstates, when we end up with more microstates than we started from, now we're growing in disorder. So delta S of the system, entropy of the system, will be greater than 0. If the number of microstates we end up with, or final microstates, are less than those that we started with, we are increasing order. Okay, so we're going down in our number of microstates. Delta S of the system will be less than 0. Okay, so it's going down. So if we end up with more degrees of freedom, we'll learn that term in just a second, degrees of freedom in the end than we started from, okay, our entropy is going up. If we end up with less, then our entropy is going down. Okay, so now let's apply this to molecules. Okay, so the number of microstates depends on the motions of the molecules. We have a couple different types of motion that we can have. So first one is translational. Okay, so this is movement of the entire molecule from one place to another. So this is like moving a molecule along a flat plane. So if you can imagine having a molecule drawn on your paper and just sort of moving it around your paper, okay, that's translational motion. So we're not rotating it, we're not pulling it closer to you, we're not moving it further away from you, we're just moving it in the plane. This is translational motion. So that's one type of microstate, or one microstate that can change. So it's a motion. Okay, then we have vibrational. This is periodic motion of atoms within a molecule. Okay, and we have a couple types of vibration. And this is where, if we were in class, I would be moving my arms around so you could see. Okay, but I'm going to do the best I can here. Okay, so we have a couple different types of motion. Okay, so we have this sort of stretch. Okay, so we have a synchronous stretch. Okay, where these two, so we have a water molecule. So we have oxygen, then we have two hydrogen molecules attached. So we have the type of stretching where the two outer molecules, or the two, atoms, two hydrogen atoms, they're stretching in sync with each other. Okay, so as this one goes out, this one also goes out with it. And when this one comes back in, this one comes back in. And they're doing this all at the same time. Okay, so this is a stretch. So that's one type of vibrational motion. Okay, so they're moving in sync with each other. Okay. Next type we have is this sort of bending. Okay, so where we have the two outer hydrogens. Okay, so they're moving in towards the center like this. Okay, and then they can move back out. Okay, so they're moving in and moving out, moving in and moving out, and they're doing this at the same time. Okay, so that's your second type of vibration. The last type we see here is when we have the same kind of stretching as we talked about at first, only this time the two hydrogens are out of sync. In other words, they're doing it independently. Okay, so as one of them moves in, the other one moves out. Okay, and then when this one retracts, this one comes back out. Okay, so they're going back and forth, back and forth, back and forth. Okay, so that's your third type of vibration. The last one is rotational. Okay, so this is rotation of the molecule on about an axis or rotation about a sigma bond. Okay, so with this particular example here, we have an axis. Okay, we have an axis rather than a sigma bond. Okay, since we're talking about water here. So if you can imagine drawing an axis right down the center of this molecule, and then rotating the water molecule around that axis, that's what we're talking about. Okay, so that's going to be our rotation. Okay, so those are the three types of motions you can have within a molecule. So translational, just moving it around in a plane. Vibrational, and you have three different types of vibrations you see there. And the last one is just rotational. So literally just spinning the molecule around an axis. Okay. Okay, this part where it's talking about sigma bonds, it's worth mentioning that that's a sigma bond. And so we could have rotation around that as well. Okay, so that's what we mean by sigma bonds. Okay, so what if we wanted to talk about ways we could increase the number of microstates and therefore increase the entropy of that particular system? Okay, so we would need to increase the temperature. If we raise the volume, we increase entropy. Volume, if we increase the temperature, we increase entropy. I think I might have said volume. Next one is volume. If we increase volume, we also increase entropy. Okay, without changing the number of molecules, if we increase volume, we increase entropy. We'll see some examples of these. Okay, and if we change the number of independently moving molecules, okay, and this can be done in three ways. Okay, so we can change the physical states of matter. So, for instance, going from a solid to a liquid. Okay, we can, if we dissolve maybe a solid into a solution, that would be another way of increasing the number of independently moving molecules. Or if we change the molecule size or the complexity. Okay, and we'll look at some examples of these next. Okay, so these are going to lead to an increase in the degrees of freedom. So I sort of mentioned this term earlier, but what do I mean by that? So a degree of freedom, or degrees of freedom, is the independent displacements or or rotations that specify the orientation of the system or body. Okay, what I mean by that is a degree of freedom is like saying one specific microstate. Okay, so if we go back to our previous slide, so in other words, these two hydrogens being extended, that's one microstate. So that's one degree of freedom. So anytime a molecule can change, that's a new degree of freedom. Okay, so let's first talk about temperature. Okay, so as we increase temperature, so as we raise the temperature, there's more kinetic energy, meaning there's more motion. Okay, so if we increase kinetic energy, we have therefore more motion, and therefore more degrees of freedom. So therefore we increase entropy. Okay, so if you think about it this way, so if we have relatively colder, so cube, so some sort of container, and we have maybe some gas molecules inside. Okay, and so they're moving at a slower speed compared to if we were to increase the temperature. So they're moving at some speed, let's just say, okay, with some velocity. Okay, so if we were to take a picture of this, okay, so we just take a snapshot of this thing, of this container. So the likelihood of finding those molecules in those positions or similar positions, okay, is more likely than if we were to say increase the temperature. Okay, so what happens when we increase the temperature? First thing we do, as it says, is we give them more kinetic energy. So we're putting energy into the system. So that leads to a couple things. First of all, our molecules are going to move faster. If they're moving faster, okay, that means they're less likely to be in the same position. Okay. Second thing is, now we have more degrees of freedom. Why? Because they're moving quicker. Okay, they have more motion. Okay, so we've basically given them more motion to translate throughout the box, okay, and to spin and everything else. And we can have some collisions, everything like that. Okay, so basically they're moving quicker, they're moving more likely to have collisions, they're therefore less likely to be found in the same position compared to the cooler box, okay, or the cooler container. Okay, so if we look at the cold box again, we have less molecular motion. We have a narrow distribution of individual molecular energy. In other words, they're all kind of moving at the same speed. Okay, they're kind of very similar. They're less random, and therefore we have lower entropy. Okay, so we have less movement, less energy, less motion. If we increase the temperature, we have greater molecular motion. They're moving around quicker. Okay, we have a broader distribution of molecular energy because we could have collisions either with the side of the container or with each other. Okay, so we're going to transfer some of the energy maybe. Okay, we're going to have more randomness because they're moving around more. Okay, so it's less likely to see them in the same position compared to the colder one. And therefore, we have increased entropy. So what you really need to remember here is that if we increase temperature, we also increase entropy. Okay, what about volume? Okay, so if we take a fixed number of molecules and we allow them to expand into a larger volume. So what are we doing here? So we have the same idea where we have two flasks connected with a valve, and then we open the valve. So same number of molecules, but now we have bigger volume. Okay, so now all of these molecules are allowed to expand into the other chamber. Okay, so now we have an increase in the number of degrees of freedom. Why? Because they simply have more room to move around now. Okay, so they have more degrees of freedom. They have more room to move around. Okay, because those are kind of the same, saying the same thing. Okay, so therefore we're increasing entropy. Okay, so the takeaway from this is that if we increase our volume with the same number of molecules, we increase the entropy because they then have more degrees of freedom because they simply have more room to move around. So it's less likely to find them in the same location. Okay, the next one. Okay, so we're talking about entropy and physical states. So as a substance goes from a solid liquid to a gas, what happens? Okay, so the first thing, the molecules or atoms have more degrees of freedom. Well, why is that? Okay, so if we look at our solid, okay, remember that in a solid, we have molecules that are very closely interacting with each other. So much so that they actually don't have any freedom within the solid. Okay, so they're sort of fixed in place. Remember, they're still vibrating. Yeah, there's still some motion there. We're not at absolute zero. Okay, but their actual motion is very much decreased. They're sort of fixed in place. Okay, so they can't squeeze past each other. They can't turn. They can't rotate. They can't really wiggle. They can't move. Okay, so they're pretty much in a fixed position. So basically what that's a way of saying is that they have a very low number of degrees of freedom. Okay, as we move to a liquid, okay, now we've increased the degrees of freedom a little bit. Why? Because now, remember, in a liquid, molecules are free to move around each other. So they still have some interaction, okay, but they can slide past each other, they can turn, they can spin, they can form new interactions, okay? So therefore, we're increasing the degrees of freedom. So now our atoms are vibrating and they're moving, they're spinning, our molecules are moving around, they're sliding past each other, and they're forming new interactions. They're all kinds of things like this. Okay, so now we have some freedom of movement. Therefore, we have more degrees of freedom as we go from a solid to a liquid. And lastly, moving to a gas, of course, this would be much higher degree of freedom, since we've said that ideally gases don't really interact with each other. Okay, so they basically have complete freedom to spin and move and turn and however they like. Okay, so this would be a dramatic increase in degrees of freedom. Okay, so as we increase or as we lower the amount of order in a system, we're increasing entropy. Those are kind of saying the same thing. Okay, but just think about it that way. So if this is the most ordered kind of matter, and this is the least ordered kind of matter, as we go from the least order to the most ordered to the least order, we're increasing entropy. Okay, and this is, I think, the last one here, making a solution. Okay, so as a solid dissolves, entropy increases. Okay, so why is that? So if we look at the example here of something like sodium chloride maybe. Okay, so we take a sodium chloride crystal. Okay, remember, crystal would be an extremely high degree of order. Okay, so this is like the most entropy you can have aside, or the least entropy you could have aside from like absolute zero, right? Okay, so we have this highly ordered crystal, and let's say we put it into water. Maybe it's sodium chloride, I don't know. Okay, so remember that it's going to start to ionize. Okay, so we're going to start to lose this crystal structure, and we're going to start to form ions. If it's sodium chloride, we form sodium ions, and we form chloride ions. And they're going to start to associate with the water molecules, okay, and they're basically going to drift wherever the water takes them. Okay, so they're no longer trapped within this crystal structure. Okay, so we start out with this nice cubic structure. Okay, then we start to lose it. It starts to become amorphous, till eventually all we're left with is just individual ions. So here's one, here's one, here's one, here's one. And notice they're no longer really associated with each other. Okay, so what have we done? We've increased their degrees of freedom by separating them from each other, by simply dissolving them into a solution. Okay, so the solute becomes more disordered, and the solvent in this case actually can become slightly more ordered if you think about it, since now we have water molecules. Okay, so now we have water molecules associated with a specific ion. Okay, so they're actually gaining order. Okay, but in this particular case, the amount of disorder strictly dominates. Okay, so going from a solid crystal to now an aqueous solution, that's going to dominate over this little bit of order we're gaining in the water molecules. So losing that crystal structure is going to purely dominate, okay, compared to that little bit of order gained by the water. This would be true with any solid dissolving, but this is a good example since we know how ordered crystal structures can be, or are, I should say. Okay, so if we dissolve a solid into a solution, we are increasing entropy. Okay, so the last one here will be entropy and molecular size. Okay, so if we have a larger molecule, there are more structural ways of bending into different shapes. So therefore, we have more degrees of freedom. So if there's more degrees of disorder, more degrees of freedom, more disorder, we have more entropy. Okay, so if we think about, we'll start from methane and we'll go all the way to propane. Okay, so what degrees of freedom do we have in methane? So first one we have translational, and I'll just draw a box. So that's just moving around in the plane. Okay, we also have some stretching that can happen. So each one of these molecules can stretch either in sync with each other or out of sync. So those are all degrees of freedom. Okay, we also have some bending that can occur. Okay, so there we can have a bend. Here we can have a bend. Okay, that's another one. We could also maybe rotate this molecule around an axis. Okay, so those are just some examples. You may be able to find others. Okay, so what if we add another atom or another set of atoms? Okay, so in this case, we're going from CH4 to CH3, or C2H6, excuse me. So we're adding an extra CH3 group. So essentially, we've popped off a hydrogen and stuck on a CH3 group in its place. Okay, so if we look at degrees of freedom here, so we always have translational. That's always true. Okay, and now maybe we can spin around this axis. We could turn around this axis. We have stretching, stretching, wiggle. Okay, but now we've multiplied each one of those stretches, each one of those wiggles, not quite exponentially, but you can kind of get the idea here. Every time we add more atoms, more atoms to the molecule, okay, we're starting to expand on those degrees of freedom, actually quite drastically. Okay, so if we look at the value here, so entropy 1.86 or 186.3 joules per mole Kelvin. So if we go to ethane, 229.6 joules per mole Kelvin. And then looking at propane, now again we've taken off a hydrogen, stuck on a CH3 group, okay, for one of the carbon groups. Okay, so again, I have translational. We always start with translational. We maybe have rotation here, we have some rotation here, we have rotation here, we have some stretching, wiggle, etc. Okay, so you can kind of see those. It's not so important that you see every single one, just that you kind of get the idea here. If you notice, again, we've increased entropy to 70.3 joules per mole Kelvin. Okay, so every time we make the molecule bigger, not only are we making it more complex, we're also making it heavier. Okay, therefore we're increasing degrees of freedom. Okay, and therefore we're increasing disorder, and therefore we're raising entropy. So the more complex the molecule, the more entropy we have. Okay, so now we're going to look at some practical applications of what we've been talking about. So here it wants you to choose the substance with the highest entropy. And this could be an example of maybe a test question I could ask you. I could just say, choose the molecule with the highest entropy. Give you a set of molecules, or just give you two like this even. That might be something I could do. Okay, so choose the molecule with the highest entropy. Okay, and in class I would just sort of walk through these with you guys, so let's just do that. Okay, so here we have solid CO2 turning into gaseous CO2, or just versus, we could say. Okay, so which will have the highest entropy? Okay, so remember, if we go from a higher order state of matter to a less order state of matter, of course we're increasing entropy. So of course this would be a gaseous CO2. Okay, next one. We have nitrogen gas at 1 atmosphere versus nitrogen gas at 0.01 atmosphere. Okay, so it might not be immediately obvious what this question is asking you, but essentially what it's saying is nitrogen at a lower volume and nitrogen at a higher volume. That's not exactly what it's saying, but it's sort of a way to interpret it. Okay. So in this case, if we have less pressure, we can expand more, the gas can expand more, have more degrees of freedom. Okay, so therefore, the gas with the less amount of pressure would have higher entropy. Okay, the next one we have oxygen gas versus ozone gas. Okay, so remember, anytime we increase the complexity of the molecule, we increase the number of degrees of freedom, and therefore we increase the entropy. Next one. Here we have liquid tin chloride versus gaseous tin chloride. Okay, so this one is sort of similar to the first one. So we're going from a more higher ordered type of matter to a lower ordered type of matter. Okay, so or phase, we could say, phase of matter. Okay, so of course the gaseous tin chloride is going to have more entropy. Okay, so here we have oxygen versus methanol, and they give you a note here. It's the same molar mass. Okay, so we're not increasing mass at all. Okay, but what have we done? So now we have CH3 attached to an OH. So we have 1, 4, 5, 6 atoms joined together versus 2 atoms joined together. So what you have to do here is you have to decide, okay, which one has more degrees of freedom? So both have translational, okay, both can have rotation, etc., and you keep thinking about this until you realize, oh yeah, so I have a more complex molecule, so therefore I have more degrees of freedom, so therefore I have higher entropy. Okay, next one. Here I have gaseous HNO3, liquid HNO3, and aqueous HNO3. Okay, so it wants to know which will have the highest entropy. Okay, so aqueous, so we've dissolved it into water. Liquid, we have it just by itself. Okay, then we have gaseous form of it. Okay, so which one's going to have the highest amount of entropy? So you have to think which one has the highest degrees of freedom. Okay, so liquid compared to aqueous compared to gas. Which one of those is going to have the highest degrees of freedom? Okay, and so of course the gaseous. Gas just has so much degrees of freedom because they're simply not, bound to anything. They can just move around however they like. Okay, one more. So here we have gaseous hydrofluoric acid, gaseous HCl, and gaseous HBr. So hydrofluoric acid, hydrochloric acid, and hydrobromic acid. Okay, so this time we want to look at what's different between these two. So we always have two molecules. Okay, but what are we doing? We're changing the halogen. And we're increasing from the lightest halogen down to a heavier halogen. So we've increased the mass, increased the size. Okay, so you can kind of think about this in terms of electron cloud size. You could kind of interpret it that way. So if we have a bigger electron cloud, we have more freedom to move around. Okay, so of course, HBr, the heaviest, is going to have the most degrees of freedom. Okay, one more. So we have gaseous oxygen at 0 degrees C versus gaseous oxygen at minus 50 degrees C. Okay, so both are quite cold. Okay, but which is going to have the higher entropy? Okay, so remember, if we increase entropy, if we increase temperature, we increase entropy. So therefore, if we lower temperature, we also lower entropy. So of course, the oxygen at 0 degrees C will have the higher entropy. Okay, one more. So we have ethylene versus nitrogen. So again, we have the same molecular mass. Okay, so molecular mass or size is not going to play a role here. What we have done, though, so we have 2 atoms of nitrogen versus 2 atoms of carbon and 4 atoms of hydrogen. So of course we have more degrees of freedom on the left-hand side since we have more options to move around. We have more options to wiggle and stretch. Okay, therefore, ethylene is going to have the higher entropy. I believe that's the last one. Yeah. Okay, so this one, it just wants us to predict the sign plus or minus for the change in entropy of each of the following processes. Okay, so again, we'll just walk through these together. So the first one, we want to predict plus or minus. So plus, we're increasing entropy, minus, we're decreasing entropy. So plus or minus. So a solid sugar is added to water to form a solution. So we're going from solid sugar to aqueous sugar. Okay, so we've dissolved a solid into water to make a solution. So of course we've raised the degrees of freedom. So therefore the sign of delta S would be positive. Oh, these are actually in there. Okay, the next one. So here we have iodine vapors condense on a cold surface to form crystals. Okay, so we're going from a gaseous state to a solid crystalline form. Okay, so if we're going to go from gas, the highest entropy, so the most degrees of freedom, down to a crystalline solid, which is some of the least degrees of freedom. So of course, we've gone down in entropy. Next one, water is heated in a microwave oven. Okay, so we said if we increase temperature, we also increase our entropy. Why? Because now we have more motion in the molecules. They're spinning more, they're stretching more, they're wiggling more. Okay, they're bumping into each other more. So of course, if we raise our temperature, we also raise entropy. Next one, we're going from solid CO2 to gaseous CO2. So this would be something like dry ice. Okay, so dry ice is just gaseous CO2, or solid CO2. And then when it heats up, it turns into gas and just kind of goes away. Okay, that's why there's no moisture left over behind dry ice. Okay, but here we're going from solid CO2 to gaseous CO2. Okay, so of course we're going from high degree of order to a low degree of order. Okay, so of course we're increasing entropy. Next one, here we have solid calcium sulfate going to calcium oxide and sulfite. Okay, so we're forming a solid and a gas. What we're also doing is we're forming 2 molecules from 1. Okay, so you have to kind of ask yourself a couple questions here. Is forming a gas enough to overtake the level of entropy from the solid? Well, sure, probably. Is forming 2 molecules more degrees of freedom than having 1 molecule? Well, of course. Okay, so we're forming 2 molecules from 1 molecule, and one of them happens to be a gas. Okay, so we've raised entropy a lot in this one, actually. So, of course, our sign would be positive. Next one, here we have nitrogen combining with hydrogen to form ammonia. Okay, so again, the Haber process, we've seen this one a lot this semester. Okay, so we're taking 2 gaseous molecules to form 1 gaseous molecule. So you have to ask yourself, would that decrease my degrees of freedom or increase? So of course it would decrease because we have 2 molecules going to 1 molecule. So of course 2 molecules are going to have more degrees of freedom. So in this case, we've gone down in entropy. Next one, we have solid iodine going to aqueous iodine. Okay, so we're dissolving iodine into water. Okay, so of course we're forming solution. And if you think back, we said that forming a solution from a solid is always going to increase entropy. So our sign would be positive. Okay, so this next slide we'll talk about what if we could have a perfect crystal. Okay, so as we slowly lower the temperature of a system, we can start to form crystals. If we were to keep lowering the temperature, molecular motion slows, and then theoretically, if we can lower the temperature low enough, it would completely stop. So if we could have, say, for instance, a crystal at 0 Kelvin, we refer to this as a perfect crystal. Okay, and a perfect crystal would have a single microstate. So we have no motion of the atoms. So no vibration, no wiggle, no turning, no twisting, no translational motion, nothing like that. Okay, so a perfect crystal would only have one microstate, so W equal to 1. So what are the ramifications of that? Okay, so if we again calculate entropy of the system, so we take our Boltzmann constant times natural log of W, our number of microstates. Okay, we put in 1. Okay, so K times the natural log of 1, which of course equals 0. Okay, so what this is saying is that at absolute 0, the entropy of the system would also be equal to 0. Okay, and this leads us to our third law of thermodynamics. Okay, so kind of a definition here. So the entropy of a pure crystalline substance at absolute 0, 0 Kelvin, would be 0. Okay, so the third law and this perfect crystal serve as a point of reference for determining entropy values. So it's sort of a way of setting the scale. So remember that with Celsius, we set, okay, the temperature of freezing water is 0, temperature of boiling water is 100. Okay, so with entropy, we've taken this idea of absolute 0 in a perfect crystal, and we've set that equal to 0 entropy. Okay, so S is equal to 0 at 0 Kelvin, simply because there's 0 degrees of freedom, or there's 0 degrees of freedom. We just have one microstate. Okay, so therefore, we have very low entropy, so low, in fact, that entropy is actually equal to 0. Okay, so that's how we define the scale. It's a reference point. Okay, so starting with a perfect crystal at 0 Kelvin, where again entropy is equal to 0, the entropy at any other temperature can be obtained by measuring the heat added to raise the temperature from 0 Kelvin. Okay, but this must be done using small and reversible steps. The change in entropy, delta S, can be expressed as delta S, the change in entropy, is equal to Q over T, where Q here is the heat absorbed and T is the temperature in Kelvin at which a change occurs. Okay, so the point when you start to see a change, that temperature, so heat absorbed over the temperature where you see a change occur, is equal to the change in entropy. So Q over T is equal to delta S. And here again, we're going to say since entropy is a state function, if we start with a perfect crystal at 0 Kelvin, so initial entropy, and warm the temperature to temperature T, S final, the following expressions are true. So we can say, again, just our state function, delta S is equal to S final minus S initial. Okay, nothing surprising there. Okay, but in this case, the change in entropy, because again, we're going from absolute 0, 0 Kelvin, okay, to some warmer temperature, of course. Okay, so we can set entropy at 0 Kelvin just equal to 0. So what we end up with is the change in entropy is just equal to the final entropy. Okay, so delta S is equal to S final. So delta S is equal to Q over T, which is also equal to S final. So because it is necessary to add heat to raise the temperature, all substances will have a positive entropy values above 0 Kelvin. Okay, so that should make sense, right? So if at 0 Kelvin, entropy is equal to 0, at any temperature higher than that, it has to be greater than 0. So determining the entropy content of matter is different from that for determining enthalpy. So for enthalpy, it is not possible to know the absolute enthalpy of content of the matter at any given moment. So we're restricted to working with delta H values that occur during any given process. So we have to study processes when we're talking about enthalpy. But unlike enthalpy, determining absolute entropy content of matter at a given moment is possible. Okay, so we can determine absolute entropy, or we can't determine absolute enthalpy. Okay, and that's simply because we've defined it where zero entropy is. Okay, we don't really know what zero enthalpy is. Okay, but we know what zero entropy is. So molar entropies for substances in their standard states are called standard molar entropies. So just like we had delta H naught or H naught, we also have S naught. Okay, so again, it's just going to be the standard entropy. So the standard state for any substance is defined as the pure substance at 1 atm and 298 Kelvin. So standard temperature and pressure. Okay, and so the units for molar entropy are going to be joules per mole Kelvin, or sometimes you'll see kilojoules per mole Kelvin, depending on how much entropy you're talking about. So here's just some basic values of entropy for you. Okay, so we have things like carbon, graphite, okay, so about 5.6 joules per mole Kelvin, moving to diamond and into vapor. So all three types of carbon here, or three different types of carbon you see here, have drastically different entropy values, moving to things like oxygen, hydrogen. Okay, you can kind of go over this list yourself, but one thing to make sure is that when you are looking up the substance, you make sure you find the correct state. So for instance, if I was looking up carbon, I chose vaporous carbon versus graphite carbon. Okay, my value is going to be completely wrong. Okay, depending on what I was looking for. Okay, but you can see, one thing you can see is that all the values are positive. And again, you can see they cover a wide range, so all the way from something like 5.6 all the way up to, I don't know, 223. Okay, so a big range here. Okay, and so this is what a table might look like of standard entropies. Okay, and on the exam, I'll give you tables like this. Okay, so for a given reaction, again, we're always going to go from reactants to products, nothing surprising there. Okay, but the change in entropy for the system can be calculated using, again, we're going to come back to our sigma notation. Okay, so delta S naught of the system, so the standard entropy of the system, is equal to the total number, so the total of the number of moles times the standard entropies of the products minus the total number of moles times their standard entropy of the reactants. Okay, we'll do some examples like this because that doesn't quite make sense. Okay, but just back to our sigma notation, just like we did with enthalpy. Okay, so again, it's a state function, so we just care where do we end up and where do we start from. We don't care about really so much how we got there. Okay, so this is how we're going to calculate delta S of the system. So total entropy of the products minus total entropy of the reactants. So let's look at how to put this equation into practice. So we'll work through sort of an example problem together, and then I'll give you a chance to work one on your own. Okay, so first, using standard molar entropies, calculate the standard entropy change, delta S of the system, for the forward reaction of the Haber process. Okay, so here we're taking nitrogen, combining it with hydrogen to get ammonia. Okay, so let's take a look at this. Okay, so first, what do we predict for the forward reaction? Will entropy increase, decrease, or stay the same? So before we looked at this, we said that we're going from 2 gas molecules to 1 gas molecule. Or maybe you could say we're going from 4 gas molecules or 4 moles of gas to 2 moles of gas. That's one way to look at it as well. Okay, we're also going from 2 molecules to 1 molecule. So we said that delta S is negative. Okay, so we said delta S was decreasing. Okay, so let's see if we're right or we're wrong. So we predict the entropy to decrease because the number of gas molecules decrease in the forward reaction. So just like we said. Okay, so let's see our calculation. Okay, so we're going to set up our equation. So our change in entropy will be the total entropy of the products minus the total entropy of the reactants. So now let's set this up. Okay, so just setting up our equation quickly. So the left side, the product side. Okay, so we're going to have 2 moles. So the product side, 2 moles of ammonia. So 2 moles times, so this 2 comes from this 2 here. Okay, so 2 moles times the entropy of ammonia minus, so just straight from our equation, minus 1 mole, so 1 mole entropy of nitrogen plus 3 moles entropy of hydrogen. Okay, so now we have to go to a chart just like the one I showed you, and we need to plug in those values. Okay, but notice these coefficients here just come down and they turn into your multiplication factors. Okay, so now inserting the actual numbers in. Okay, so you just again go to a table like the one I showed you and pull these numbers. Okay, so now we just have 2 times this number of joules per mole Kelvin minus 1 times this number we again looked up in the table plus 3 times 130.6. Okay, so just pulling those numbers straight from the table. So you just go and you find, for instance, gaseous hydrogen, gaseous nitrogen, gaseous ammonium, and find those numbers. Okay, and all it's left to do is just to solve out the math. So do this multiplication and addition, and then do the subtraction. Okay, so you end up with something like this. So 2 times 192.5 gets you 385 minus, okay, so just carrying down the minus sign, okay, minus 1 times 191.5 is just 191.5 plus 3 times 130.6 gives you 391.8. Okay, so then add those two together, and then you can do your subtraction. Okay, so that leaves us with 385 minus 583. So you end up with an entry of minus 198.3 joules per Kelvin. So our sign, negative. So our entropy went down, just like we said. Okay, so that should hopefully give you an idea of how to set up the sigma type problem. So the sigma notation should give you an idea how to set that up. And then it's just calculating the change in the entropy. It's not too tough here. Okay, so we'll talk about what exactly the sign means in just a few minutes. So remember, we always said that entropy has to increase, right? So we're talking about entropy decreasing, and I told you this was the Haber process, and we discussed sort of the importance of that before. Okay, but now I'm telling you the entropy in the Haber process is negative. But wait, entropy can't be negative, right? Okay, so we'll talk about that in a second. First, give this one a try. So go ahead and pause your video. You have a table of values here. So go ahead and pause the video and try to give this one a try. Okay, so hopefully you've had a chance to attempt this problem now. What I will do is I will now just drag the problem over to a workspace for us. Okay, and let's set this up. Okay, so we're going from liquid ethanol. So we're going from liquid ethanol, grab a pencil. Okay, so we're going from liquid ethanol to gaseous ethanol. Okay, so that's what we want to look for in our table. Okay, so if we come over here to our table, okay, so first thing we want to do is we want to look for ethanol. So C2H5OH, so just ethanol. Okay, and we see two different types here. Okay, so we see gaseous, and we see liquid. So let's just go ahead and write down those values. Okay, so let's just write them under for sake of simplicity. Okay, so let's just follow this across. So we have 160.7 and 282.7. Okay, so 160.7, and if you check your units, again, that's joules per mole Kelvin. Okay, then for gaseous ethanol, we have 282.7 joules per mole Kelvin. Okay, and that should make sense since we're going from a liquid to a gas, we're increasing entropy. Okay, so that should make sense. Okay, so now let's set up our equation. So remember, we're using this equation. So we're going to say delta S naught, since we're talking about standard entropy, and we're talking about of the system, it's going to be equal to, so sigma times N times S naught for the products minus sigma And we'll just say M here since it has to do with the other side. Okay. So times S naught of the reactants. I'll just write react for now. Okay, so that's our equation. So now we just need to fill this in. So this one's relatively simple. Okay, so we just have 1 mole of each. Okay, so now let's just fill it in. So we're going to say delta S of the system is going to be equal to, and these brackets are used because a lot of times you have multiple things on each side. Okay, so let's look at our products. So here we have 1 mole of gaseous ethanol. So we'll just say 1 mole times, and then just grab our delta S, or our S value. So for now, I'll just write S naught of CH3, OH, and that's our gas. Okay, so that's our product side. Now let's look at our reactant side. Okay, so again, we have 1 mole, okay, times, and then we're going to say our entropy of CH2, CH3, OH, but now we have the liquid form. Okay, so that's our equation. Now we just need to substitute everything in. So I'll just slide this up. So we can see our values still. That would be helpful. Okay, so now let's just plug everything in. So delta S, the system, is going to be equal to 1 mole times, again, we're talking about products here, so 282.7 joule per mole Kelvin. So you can probably see how these equations start to get kind of long here. Minus 1 mole, then grab our one for our reactants, 160.7 joules per mole Kelvin. Okay, and then all that's left is just to plug this into the calculator. Okay, so essentially what you end up with is delta S naught for the system equal to 282.7 joule per mole Kelvin minus 160.7 joule per mole Kelvin. Okay, so basically, since we just have 1 mole on each side, essentially you just have the 2 entropies subtracted, or, taken from each other. Okay, so if you do this math, you end up with delta S for the system equal to 122 joules per mole Kelvin. Okay, so this would be your final answer. Okay, and I'll zoom out here for you so you can see the whole problem. Just double check how that's looking. Zoom out a little bit further. Hopefully I wasn't off the screen there just now. I apologize if I am. If I was, to make a note of that. Okay, so but now you can see the whole answer. So hopefully your answer looks something like this. Okay, so going back to our slides. Okay, and now here we have another problem. Okay, so give this one a try. So I'll go ahead and pause the video, try to work it out. It's very similar to the last problem. Now it's just a little more complex. So you're dealing with more substances. Okay, the base of the problem doesn't change. You're still going to use the same equation. Now you just have to understand how to put all these different components in. Okay, so you have your reaction equation, and then you have a table that should have everything you need. Okay, so go ahead and pause the video and give this one a try. Okay, so hopefully you've had some time to give this problem a try. So let's jump to our workspace again. Let's go over this. Okay, so here's our problem. Okay, so we have, they want us again to calculate standard entropy and calculate delta S using the values from Appendix C. Okay, so change in standard entropy and calculate delta S. Okay, so here we have sort of a little bit different problem. Very similar, but a little different. So we have methanol combining with oxygen to give us CO2 and water. So we have a combustion problem. So we're combusting ethanol with oxygen, of course, to give us our standard combustion products, carbon dioxide and water. Okay, so the first thing we want to do, let's just grab our entropy values. Okay, so first let's look for gaseous ethanol. Shouldn't have changed from last time. So 282.7. I'm going to leave off the units now, so we should know those. So I'm going to leave them off for this moment. Okay, then we have gaseous oxygen. Okay, so here, 205.0. Okay, now we have gaseous CO2. Okay, we come over here, we find that here. Okay, 213.6. Okay, and then we have gaseous water. Okay, so let's find that in our chart here. Okay, so 188.83. Okay, and those are all going to be in terms of joules per mole Kelvin. Okay, so remember your equation is just going to be the same thing here. So we're going to say delta S naught of the system. That's what they're asking us to calculate. Okay, it's just going to be equal to total entropy of the products minus, oh, that's not a great looking sigma. Try that one again. Okay, so a little better, not much, but you get the idea. The total entropy of the reactants. Okay, so now we just have to kind of fill in our equation here. Okay, so I'm going to jump a little bit down here to the bottom so we have a little more space. Okay, but we can see everything we need. Okay, so I'm going to say delta S naught of the system is going to be equal to, and we'll start from our products. We always start from the products. So 2 moles, so just starting from CO2 times S naught CO2 plus, because we're talking about sigma, so this is going to be our addition part. Okay, so plus 3 moles times, and then we're talking about water here, so the 3 comes from this coefficient, and then just times 188. Let's actually just stay with our S for now. So S naught of water, and of course we know what water we're talking about. Okay. Okay, so minus. Okay, so now we're going to look at our reactants. Okay, so the first one we just have 1 mole times S naught for ethanol. Okay, of course, again, we know we're talking about gaseous ethanol, so you don't have to really write your state in. Plus, again, we're talking about sigma notation, so we're going to say plus. Okay, and then 3 moles times S naught of O2. Okay, so that's our base of our equation. So now we need to fill in our actual entropy values. So you don't have to write it out with the S's in every single time, but it is a little helpful just to make sure you're kind of setting up the equation correctly. So now let's fill it in, because as you can kind of see, these equations are going to get bigger and bigger. They're going to get longer and longer. Okay, so now let's add in our entropies, and you'll see what I mean. Okay, so we're going to say delta S naught of the system will be equal to. Okay, so we'll fill in our left-hand side, products. So S naught of CO2. Okay, so here. Again, your units are joules per mole Kelvin. One thing I find handy when doing these problems is just to maybe put an X or a line under the value once you use it. That way you know not to use it again. Plus 3 moles times S naught of water, so 188. Okay, so that's our total on our product side. And I'm just going to write below it, so I'm going to say minus. So just continuing the problem down because there's not enough room to write over there. Again, we use this value, so let's write an X. Okay, now we'll carry this section down. Okay, so just use a little highlighter here, so that doesn't quite show up, does it? Let's do this. Okay, so this section goes here. Okay, so now we're dealing with, let's say blue. Now we're dealing with this section. Okay, so it's going to go below. Let's grab our other color. There we go. Okay, so now let's fill in the rest of the equation. Okay, so now we're going to say 1 mole times, I'm using a different color or a different size, aren't I? Let's stick with the same one. So times 1 mole times S naught of ethanol, 282.7 joules per mole Kelvin. You can kind of leave the units off once you get used to doing these, but it's good in the beginning to make sure you write your units so that you don't forget them. Where did my page go? There we go. Okay, so plus, I'm going to say 3 moles times S naught of oxygen, so we use this one. So it's going to be 205.0 joules per mole Kelvin. Okay, and that's our total on that side. Okay, so this side, that's our blue side of the equation. Okay, so hopefully that helps a little bit to show you what I'm doing here. So I'm just breaking the equation in half, and you'll probably have to do this on your paper as well, unless you write really, really tiny. Okay. Okay, so now let's actually solve this problem. Okay, so if you go through and you do the addition, you do the multiplication, you do the addition, you should end up with something that looks like this. Okay, so you should end up with, can you guys still see? Yes, okay. So you should end up with delta S naught of the system. Okay, we're at standard conditions. We're talking about the system. So I ended up with 993 point, let's just keep, how many sig figs should we keep here? Let's just take 2 after the decimal for now. 0.69. I'm going to say minus 897.7, and this is joules per mole Kelvin, of course. Joules per mole Kelvin. Okay, then actually solving this problem, you end up with an answer of 95.99 joules per mole Kelvin. Let's fix that real quick. Okay, so that would be your delta S naught of the system. And do we have the right amount of sig figs? Sorry, I keep accidentally going to desktop there. Let's see, here we have 1, 2, 3, 4. 1, 2, 3, 4. Yeah, so it looks like 4 is going to be the smallest number here, so this would be our final answer. Okay, and I will zoom back out. So you can see the whole problem. So what's nice about this is I can actually save these as a PDF for you, and I will upload those along with slides and everything on the Blackboard for you. So you can actually have this on your computer, so you can actually zoom in if anything's unclear or anything like that, and you can rewind the video and all that kind of good stuff. I don't think I can show you in actual real time, but I can show you the static document. Okay, so moving back to our slides here. So we've been talking a lot about delta S of the system, so entropy of the system. We haven't really mentioned delta S of the surroundings. Okay, so remember we have system surroundings and we have the universe. So the universe contains both the system and the surroundings. Remember we said that delta S of the universe must always be increasing. Okay, so we've shown that delta S of the system sometimes is increasing. We looked at Haber-Bosch process where it's actually decreasing, which is interesting. Okay, so let's take a look at how that can be true. Okay, let's look at delta S of the surroundings first. So how do we get delta S of the surroundings? So for this one, we have to do sort of derivation. Okay, so we have to derive it. Okay, so if we say that under isothermal conditions, in other words, so ISO 1 thermal heat, right? So under constant temperature, isothermal, we can say delta S of the surroundings is equal to the heat of the surroundings over the temperature. So remember Q, heat, work, kind of interchangeable there, over temperature, not exactly the same thing. Okay, so given that, Q of the surroundings has to be minus Q of the system. So the heat of the surroundings must be equal and opposite to heat of the system. We can say this. So we can say delta S of the surroundings is equal to minus the heat of the system, so minus Q of the system, over T. Okay, so remember Q is heat. Okay, and then under isobaric conditions, so this is at constant pressure, so isothermal is at constant temperature, isobaric is at constant pressure, we can say that Q of the system is equal to delta H of the system. Okay, so the heat of the system is equal to the enthalpy of the system. So therefore, we can come up with this. We can say delta S of the surroundings is equal to minus delta H of the system over temperature. And this is going to be at constant temperature and pressure. Okay, so this is important. So we're not changing our temperature or not changing our pressure. So if we want to calculate delta S of the surroundings, we're going to use this equation. So minus enthalpy of the system over temperature. Okay, in other words, if we're losing heat from the system, where does it have to go? It has to go into the surroundings, right? Okay, so if we're moving it from one place to the other, okay, we know it's going to have the same magnitude, just a different sign. Okay, so once one part is losing it, the other must be gaining it. We saw that before. Okay, so we can make this equation. Delta S of the surroundings equal to minus delta H of the system over T. So suppose we wanted to calculate delta S surroundings for the Haber process. So remember, we looked at delta S of the system. I said it was negative, and that was sort of interesting to us because we said, wait, entropy always has to increase. Okay, but we showed that it decreased. Okay, so let's take a look at this. So here again we have nitrogen plus hydrogen gives us ammonia, and that gives a delta H value. So just set up our equation. We want to know delta S surroundings. Okay, so we're going to set up our equation. So delta S surroundings will be equal to minus delta H of the system over temperature. Okay, they were nice enough to give us delta H here. Okay, so all I have to do is plug it in. So delta H for this process is equal to minus 92.38 kilojoules, and that's at 298 K. Okay, and that's nice because they asked us at 298 K, so we can actually use that value. Okay, if it was at different temperatures, we couldn't use that value. Okay, so just plug in. So minus delta H, so minus 92.38 kilojoules over 298 Kelvin. Okay, then we just have to solve the math there. Just plug it into your calculator. So it's going to be equal to 0.310 kilojoules per Kelvin. Okay, so delta S of the surroundings is increasing. Okay, so increasing by about 310 joules per Kelvin. Okay, so pretty dramatic increase here. So if you remember earlier, delta S of the system for this process was minus 198.3 joules per Kelvin. So if we look at how much is lost by the system and how much is gained by the surroundings, so the amount of entropy lost by the system, minus 198.3 joules per mole Kelvin. So it's more than compensated for by the entropy gained by the surroundings, which is 310 joules per mole Kelvin. Okay, so overall, we're increasing entropy. So the process is still allowed. So even though the entropy of the system decreased, the entropy of the surroundings increased, so therefore, delta S of the universe is still increasing, so we have an allowed process. Okay, so if we just put this together, so we say delta S of the universe is equal to, so this was our delta S of our system plus delta S of our surroundings. Okay, you can put these other way around, just make sure you change your sign. Okay, best to write them this way though, so just say system and surroundings, that way you know what sign to put in the middle there, don't confuse yourself. Okay, so let's just say delta S of the universe is equal to minus 198.3 joules per Kelvin plus 310 joules per Kelvin. So that's going to give us a positive 112 joules per Kelvin. So if we go back to our second law of thermo, okay, so delta S of the universe, or let me rephrase, so our second law of thermo applies to delta S of the universe. So exactly what I said on the last slide. So we know that delta S of the universe has to be increasing. So since delta S of the universe for this process is greater than 0, the process is spontaneous and allowed. We'll talk about this term spontaneous a little bit towards the end of the chapter. Okay, but for now we're really just interested in this term allowed. Okay, so since we increased entropy, we have an allowed process. If we didn't increase entropy, we would not have an allowed process. Okay, so here's another one for you to try. Okay, so here it says consider the oxidation of iron metal. So we have iron combining with oxygen to give us iron oxide, and they give us some delta H values, they give us some entropy values. And it says, by determining the sign of delta S universe, show that the reaction is spontaneous at 298 K. Okay, so go ahead and pause the video, give this one a try, and when we pick back up, I'll go over it with you. Okay, so switching back over here to our workspace, let's give this problem a try. So here's our problem again. Okay, so this should be similar to what we just looked at. What they want us to do is they want us to first basically calculate delta S of the universe and show that the reaction is spontaneous. Grab a little bit thicker pencil here. That'd be a little easier for you to see, hopefully. Okay, so let's work this problem out. Okay, so it's asking us to calculate delta T of the system. Just one second here. Just don't erase part of the problem. Okay, here we go. Okay, so the problem wants us to calculate delta S of the universe. Okay, so remember, delta S for the universe is going to be equal to delta S of the system plus delta S of the surroundings. And again, just keep them in this order so that you know what you're working with here. Okay. So we have to do two calculations here, unfortunately. So we first have to calculate delta S of the system, which again, remember, is equal to okay, so total entropy of the products minus total entropy of the reactants. I can write that a little bit neater, I think. Okay. And we also need to calculate delta S of the surroundings. Okay, so a little bit of a long problem, but nothing really changes in these two calculations. So you're going to calculate them exactly the same as you did when they were split apart. Okay, so you have your delta S surrounding equation, your delta S system equation. Okay, so remember this is just minus delta H, the system, over your temperature. Okay, so let's start out by calculating delta S of the system. Okay, so a little bit longer part. Okay, so let's just set that up. Okay, so I say delta S system, delta S naught of the system is going to be equal to, okay, so let's just write all this out. So we're just going to grab our equation and start to plug everything in. So remember, it's the products, so we have 2 moles times S naught for iron oxide. Okay, so that's the first part, minus, now we have 4 moles of iron, okay, plus 3 moles of oxygen. Okay, so that's our equation. Now we just need to fill in our entropy values. And they went ahead and gave those for us. That was nice. Okay. So here, let's just plug them in. So 2 moles times entropy for iron oxide. Just come up here and grab it. Okay, so 87.4. Remember, these are joules per mole Kelvin. Minus, and I'll just, again, go ahead and cross this out since we used it. Minus, and maybe we can squeeze this in. Okay, so minus. Okay, so we're going to have 4 moles times, we'll start with iron here, so 27.3 joules per mole Kelvin, plus 3 moles times 205.0. Squeeze in my units there. Okay, that's my whole equation. So then go in and do this multiplication, and then do the addition, and you end up with this. So you end up with delta S for the system is equal to 174.8 joules per mole. Oh, sorry, joules per Kelvin in this case, because the moles will cancel out. Minus 724.2 joules per Kelvin. Okay, so you end up with a final answer here of delta S naught of the system equal to minus 594.4 joules per Kelvin. Okay, so that's part of our answer. And I'll slide our page up a little bit. Try to keep our values where we can see them. Okay, now we need to calculate this part. Okay, so now we need to calculate delta S of the surroundings. Okay, so we'll say delta S of the surroundings is going to be equal to minus delta H of the system over T. So this will be equal to, they gave us our delta H up here, so minus 824.2 2. Very important to keep your signs straight here because you're going to get a whole different answer if you don't. Okay, over T, and that what temperature did they give us? They said 298 K. Good, that's what we want. So 298 K. Okay, and our units here are going to be kilojoules per mole. Okay, sorry, I had to take a little bit of a pause there. But let's go back and try to finish this problem up. Okay, and let's just take this unit as kilojoules. Okay, but something I want to do here is I actually want to first, let's change, well, let's just keep this the same for now. Okay, so this is going to end up giving us value of okay, and so the change I made there is I wanted to keep this as kilojoules. So they gave it to us in kilojoules per mole, but right now we're not really concerned with kilojoules per mole per se. So let's just take that value as kilojoules for now. Okay, so that we can have our units line up in the end. Let's just keep it as kilojoules. Okay, so this ends up giving you 2.766 kilojoules. That's over Kelvin. Okay, but you notice that here we're in kilojoules and up there we're in joules. Okay, so now we need to convert our unit here. Okay, so we have 2.766 kilojoules per 1 Kelvin. Okay, so setting up our dimensional analysis here. Remember that there's, for every 1 kilojoule, oh, that's not great, let me fix that. Every 1 kilojoule, there's 1,000 joules. Okay, bottom stays the same. So this gives us 2,766 joules per Kelvin. Okay, so this is for the surroundings. We have the value for the system. Now we want to know delta S universe, which will be equal to, if we come back up here to our equation, so the system, delta S of the system, okay, so minus 594.4 joules per Kelvin plus 2,766 joules per Kelvin. Okay, so delta S of the universe will be equal to 2,216.6 joules per Kelvin. And using correct sig figs here, let's see, how many can we take? We can take, what, 3? Okay, so this, we'll say this is about 2,220 joules per Kelvin. We're saying that this is about equal to, not necessarily equal to, so roughly equal to. Okay, and so now we need to look at what the question is actually asking us. So let's go back up. So it says show that the reaction is spontaneous. So we calculated delta S universe. Now we want to know, is this reaction spontaneous or not? So remember, we said that for a reaction to be spontaneous and allowed, delta S has to be increasing. In other words, delta S has to be greater than 0. Okay, so what we want to know in this equation is 2,216 or 2,220 joules per Kelvin greater than 0. And of course, 2,220 joules per Kelvin is greater than 0. So delta S of the universe greater than 0. In other words, it's increasing. So it asks us spontaneous, right? Is it a spontaneous process? Yeah, sure. So yes. Okay, so this would be your final answer. Okay, so kind of zoom in on parts of this for you so you can see it. Probably getting mad at me for moving around too much right now. I'll try to stop doing that. Okay, so there's the top part. Okay, and then here's the bottom part. And again, I will save this as a PDF for you and put it up on the Blackboard. Just make sure you can see everything. The bottom part's a little bit cut off. Okay. So let's go back to our slides. And I think that is going to be a good place to pause. I know that's a lot to digest. Okay, so now we put the math to those concepts. So we started from just sort of these abstract concepts, and now we put math with it. So I think next time, let's go ahead and pause on entropy here, and next time we'll pick up with Gibbs free energy, and we'll finish out thermodynamics.